Alright folks, this is the first half of problems of the gas law and Stoich problems. We're specifically looking at problems 1 through 4. Okay, these are rather long. Right. Solid potassium chlorate decomposes to produce solid potassium chloride and oxygen gas. So what we have to do is, the first thing we have to do is come up with our chemical equation. Alright, so our chemical equation is potassium chlorate, KClO3, decomposes into potassium chloride and oxygen gas. Oxygen is a Brinkelhoff element, so it is O2. Let's see, we're not balanced, but we do have potassium's positive 1, chlorate's minus 1, so it's KClO3, and potassium chloride is positive 1 minus 1, so those cancel, so that's good. So we've balanced our charges, but we have to go and balance our oxygens. So we do that by putting a 2 and a 3, which means we need 2 potassium chlorides. Right, so what's it asking us for? It's asking for volume of oxygen gas. So we'll probably do that in liters, measured at 40 degrees Celsius and 655 millimeters of mercury. We have 13.5 grams of potassium chlorate decomposing. Well, since we're trying to find volume, what we would have done is we just would have done a Stoich problem and used 22.4 liters for our volume, but we can't do that anymore because we're not at STP. So we can still do a Stoich problem to figure out the number of moles of oxygen we produce, and then we can figure out how much volume those moles of oxygen will take up. So let's do that. Okay, we have 13.5 grams of potassium chlorate, so that's over here, so we have to figure out how much potassium chlorate weighs. So we take KClO3, and that's going to be, let's see, I'm going to let you do that, but that's 1 potassium at 39.1 and 1 chlorine at 35.453 and 3 oxygens at 48. So that's going to give you a molar mass of 122.55 grams per mole. Alright, so that's potassium chlorate. So now the next thing we have to do is, well, let's see, while we're in conversion mode, let's do 40, we have 40 degrees Celsius, and we add 273 to that, and that gives us 313 Kelvin. Let's see, the other thing we can do, well, let's wait a minute, we'll do that in a minute when we decide what R constant we want. Okay, so now we're going to do our Stoich problem, where we start with 13.5 grams of potassium chlorate. Well, you have to get rid of grams of potassium chlorate. And go to moles of potassium chlorate. Well, we don't want moles of potassium chlorate, we have to figure out moles of oxygen. So we have to go from moles of potassium chlorate to moles of oxygen. And let's see, 1 mole of potassium chlorate we just figured out weighs 122.55 grams. And our moles of potassium chlorate, for every 2 moles of potassium chlorate, we produce 3 moles of oxygen. So we have a 2 to 3 ratio there. When we actually do that math out, we get 0.165 moles of oxygen. Okay, so now what we want to do is we want to do pivnert. But to do pivnert, we need to pick an R value. Let's see, if we want our answer in, if we want our volume in liters, and let's say that I'm going to go, and that's what I tend to use is liters, all right? So then I'm going to use the 0.0821 R constant. So PV equals nRT. Now, to use that R constant, we have our pressure in millimeters of mercury. So let's convert that to atmospheres. 655 millimeters of mercury. It's almost 1 full atmosphere. No, it's not. 760 millimeters of mercury in 1 mole in 1 atmosphere. So 760 millimeters of mercury, 1 atmosphere. We want the thing in atmospheres, so when we go and do this division, we get 0.862 atmospheres. Alright, so now we can do pivnert. We're trying to figure out our volume. So our volume is nRT over P. So the number of moles we have is we have 0.165 moles of O2. And our R constant is going to be 0.0821 because we wanted our answer in liters, atmospheres, moles Kelvin, 100 liters, and let's see, our temperature is, what do we say, 313 Kelvin. We divide this by our pressure. Our pressure has to be in atmospheres, 0.862 atmospheres. All right, and why does it have to be in atmospheres? Well, because up here in our R constant, it is in atmospheres. So we cancel our atmospheres. We cancel our moles. We cancel our Kelvin. So we're left with liters, which is what we want as an answer. When we do all the math out, we come up with 4.93 liters of oxygen gas. That's our answer. Okay, how many grams of water are produced when 500 liters of hydrogen gas is measured? It's ignited with oxygen. Okay, so the first thing we have to do is come up with our chemical equation. So our balanced chemical equation is hydrogen gas plus oxygen gas gives us water. And to be able to balance our equation, we have to put 2's in front of our h's. Okay, so there's our balanced chemical equation. Let's see, we have how many grams of water? We're trying to calculate grams of water. To be able to do that, we have to figure out, oh gee, how much 500 liters, how many moles 500 liters of hydrogen gas is? Well, because we're not at STP, we have to go and do some conversions. So let's convert some stuff so that we can actually use information. 0.97 is already ATM, so that's helpful. So we can use our regular R constant for that because we have liters, and that's the constant we would want to use because of liters. We only have to convert 25 degrees Celsius. So we do that by 25 plus 273, gives us 298 Kelvin. Right? So that's pretty much our only conversion factor we have to do. So let's see, PIV PV equals nRT, and we are trying to solve for N because we're trying to come up with the number of moles of hydrogen. So N is equal to PV over RT. So our pressure, which has to be in atmospheres, is 0.97 atmospheres. We're going to have 2 sig figs in our answer. All right, and let's see, our volume is 500.0 liters, and our R constant, because this is liters, is going to be 0.0821 liters, atmospheres, moles Kelvin, and our temperature is going to be 298 Kelvin. Let's check our units, make sure they cancel. We have Kelvin going, we have liters going, we have atmospheres going, and so we're left with moles, which is great because that's what we want N to be. So we do our math, and we figure out that that's 19.8 moles of H2. All right. Let's see, let's keep going now. So we now take our 19.8 moles of H2, and now we have to convert moles of H2 into moles of water. Actually, we want to have grams of water, right? Because we asked for grams of water. So let's go and get to grams of water. 19.8 moles of H2. I don't have to worry about grams of H2, I just have to worry about moles of H2. So I can go from moles of H2 to moles of water. But I don't want moles of water. I have to go to grams of water. Right. So I have, let's see, I have 2 moles of H2 give me 2 moles of water, so that's 2 to 2. And moles of water going to grams of water, well, you should know the grams of water is 18.015 grams per mole. If you don't know that off the top of your head, you should be able to calculate it. Okay, so we multiply that out, and that gives us 357. Or because we have to go with only 2 sig figs because of our atmospheres, we're going to end with 360 grams, right? Grams of water. All right, that's it for number 2. Number 3, 500 grams of carbon disulfide burns. Now let's start with this. Carbon disulfide. Carbon disulfide burns in the presence of oxygen. Let's see, to produce carbon dioxide, CO2, and sulfur dioxide, SO2. All right, well, we don't have to worry about balancing our charges because these are all covalent, and it told us what they were. So let's see, we have 2 sulfurs on the left, we have to have 2 sulfurs on the right. That means we have a total of 6 oxygens. We have to put a 3 over here. So I think we're now balanced. So let's see, what do we have? We have 500 grams of this stuff burning, and how many liters of sulfur dioxide is... All right, so we're going to have to calculate how many moles of sulfur dioxide we produce. Okay, so we're going to start with grams of carbon disulfide. How much does carbon disulfide weigh? That's 12.011 plus 2 times 32.06. And so we're going to figure out that carbon disulfide weighs 76.13 grams. 3 grams. That's because I used 32.066, and then I rounded. 76.13 grams per mole. And we've got 500 grams of the stuff, so we get a bunch of it. So let's go and convert that into moles. 500 grams of carbon disulfide. And I have to convert from grams of carbon disulfide to moles of carbon disulfide. Am I done? No, I have to go from moles of carbon disulfide to moles of, what do I want? I want moles of SO2. All right, so 1 mole of carbon disulfide weighs 76.13 grams. And I have 1 mole of carbon disulfide producing 2 moles of sulfur dioxide. Okay, so that's going to give me 13.1354 moles of SO2. Now guys, I realize I can't take that many sig figs with me, but I'm doing it just to make sure that I don't lose precision and use and have rounding errors that I compound by doing them multiple times. All right, now what I have to do, I have to notice I'm at 27 degrees Celsius. 27 degrees Celsius. And I'm over water. Oh gosh. So this pressure that I have of 740 millimeters of mercury includes the water. So let's see, I'm at 27 Celsius, so I have to figure out what my water vapor pressure is. So let's see, 27 degrees Celsius and 27 degrees Celsius. I come over here and I look at my number, and it's 26.7 millimeters of mercury. Okay, so if I have 740 millimeters of mercury, let's do it over here, 740 millimeters of mercury, and I have to subtract, what did I say I was subtracting? Got it already? What was my number? 26.7. 26.7 millimeters of mercury. Right? Then I get 713.3 millimeters of mercury. All right. So let's see. Now what do I want to do? Well, that tells me the 73.3 millimeters of mercury is my pressure of my sulfur dioxide, because the 26.7 was the pressure of water. So when I do my PIV-NERT, I have to use this, the 713 millimeters of mercury, as my pressure. Well, let's see. I'm asked for liters, so when I do PIV-NERT, I'm going to use 0.0821, which means my pressure needs to be in atmospheres. So let me convert the 713.3 millimeters of mercury into atmospheres, and I do that by dividing by 760 millimeters of mercury in 1 atmosphere. And when I do that, I get 0.9385526 atmospheres. Again, guys, I understand that I can't hold all those sig figs, but I'm going to do it now anyway, just because it's easier. Okay. All right, let's see. What do I get? Okay, so I've got atmospheres. I'm looking for liters. My temperature is at 27 Celsius. I haven't done that yet. 27 Celsius plus 273. Well, that's a nice round figure of 300 Kelvin. Right. Is there anything else I've missed? I should be able to do PIV-NERT now, I think. PV equals nRT. And I want to do volume. So that's nRT over P, which is equal to my number of moles. Let's see, where's my number of moles in this mess? moles. There we go. So my number of moles is 13.1354 moles. And my R is 0.0821, and I want to do liters, atmospheres, moles Kelvin. And my temperature is going to be 300 Kelvin. And my pressure is going to be 0.9385526 atmospheres. Let's see, my atmospheres cancel, my Kelvin cancels, my moles cancel, so I'm left with liters, which is good because that's what I want my volume to be in. And when I'm all done, I multiply all this out, I get about 345 liters of SO2. We probably have to go and take that down to 2 sig figs because of this guy, but so it's 350 or maybe 340. I don't remember how I rounded. But anyway, that's your answer. All right, this is going to be the last one for this podcast, and then you can do the other one if you need to. Right. We're given the chemical equation. This is the chemical equation of sucrose burning, also known as respiration. This is what our bodies do. How many grams of sugar will be needed to make 54 milliliters of carbon dioxide at this temperature and pressure? All right, let's see. We're using milliliters, so we can convert milliliters to 0.054 liters. That's really easy because there are 1,000 milliliters in a liter. We have 550 degrees Celsius, which we add 273 to that, and we get 823 Kelvin. And we already have 8 atmospheres, so that's really easy. And we're going to end up with only 2 sig figs because of this thing. Actually, because of all of it. All right, so let's go ahead and do this. We have... Let's see, what do we do first? Do we do Pivnert first? Do we do moles first? What do we do? Do we do Stoich first? Think about that for a second. Well, we're trying to calculate how many grams of sugar we have, but we're starting with all of this stuff that's a gas. And since we're starting with stuff that's a gas and it's not at standard temperature and pressure, the first thing we're going to have to do is Pivnert. Right, and we have to figure out how many moles of gas we're producing. So that's N is equal to PV over RT. And so your pressure is going to be 8 atmospheres. Your volume is going to be 0.054 liters. Your R is going to be 0.0821 liters, atmospheres, moles Kelvin. And your temperature is going to be 823 Kelvin. Now guys, you may say, well, why in the world did he go with 0.054 liters instead of milliliters? Who cares? Well, this cares. You'll notice this unit here is in liters, and this unit here is in liters, and they have to match so that you can cancel them. And your atmospheres cancel, and your Kelvins cancel, so you're left with moles. It's very important that you always match your units. Right? So when you actually do this, you get 0.06335 moles of, in this case, it's CO2, is what we produced. Now, we have to work backwards to figure out how many grams of sugar that is. Well, what we have to do is figure out the molar mass of sugar. Well, if you sit down and do the molar mass of sugar, 6 carbons, 12 hydrogens, 6 oxygens, I'm not going to waste your time with that. Right? That's a total of 180.17 grams per mole, which is very important as we try and figure out the rest of this problem. Because we're starting out with 0.00633935 moles of CO2. Now we have to convert from moles of CO2 to moles of sugar, C6H12O6. But then we have to convert from moles of sugar to grams of sugar, because that's what the question asked for. All right, well, let's see. We know that 1 mole of sugar we just calculated, that's 180.17 grams. And we know that, let's see, we have 1 mole of sugar and 6 moles of carbon dioxide. That's our ratio. 6 carbon dioxides to 1 sugar. So I actually do the math here. When I come up with it, I come up with 0.192, or maybe just 0.19 grams of sugar. Right? So that's our answer. That's it for this podcast. If you have questions, please see us in class. We're going to move on. If you want to watch the rest of the questions, just go on to the next one. Okay? See you in class. Have a great day.